Today I am going to explain electric potential difference. I am going to explain what electric current is. In fact, all these titles are explained in the 11th grade in 3 chapters, but I don't have so much time. So just in 5 lessons, I am planning to explain all the required information for 12th grade. Before I start explaining electric potential difference and electric current, I will now first talk about types of materials. So some materials are conducting electric current. Some conductors cannot conduct electricity. So according to what atomic structure, some materials are conducting electricity, some cannot conduct electricity. So I will talk about this. And also, this short title is going to be a part of chapter 9. So according to the behavior of electrons of atoms, so we are going to check the behavior of electrons, and this is the keyword. Materials are divided into 3 groups. First group of materials are conductors. Second group of materials are insulators. Third group of materials are semiconductors. So first I will explain conductors. What atomic property of a material makes a substance conductor. In conductors, electrons are freely move from one atom to another one. Now in this diagram you see 3 atoms. And of course, we know atom structure of an atom. There are protons inside the nucleus and neutrons. And electrons are revolving around the nucleus in circular orbits. Just like planets are revolving around the sun. But in conductors, the outermost electrons, outermost means, the electrons at the outer orbit are able to jump from one atom to the next. From one atom to the next, they can. So that's why we say that outermost electrons of conductors are mobile. Mobile means can move from one atom to the next. By the motion of these electrons, from one atom to the next to the next, so electricity is conducted through a conductor. This is structure of a conductor, how conductors conduct electricity or let electricity to flow in the conductor. Most metals are conductors, such as copper, aluminum, silver, gold. So these are conductors. They conduct electricity. Second group of the materials are insulators. Structure of the insulators, atomic structure of insulators are different than the atomic structure of conductors. How? Electrons in the atoms are unable to move from one atom to the next one. They cannot. This atom cannot jump to the next atom, or this electron cannot jump to the next atom. Electrons, outermost electrons are not able to move from one atom to the next. So outermost electrons, electrons in the outer orbit are immobile, unable to move. So if charges are unable to move, if electrons are unable to move from atom to atom, so electrons, these materials cannot conduct electricity, which are called insulators. Good example for insulators are glass, rubber, silk, plastic, paper. So these are materials which cannot or do not conduct electricity, called insulators. Third group of material is semiconductors. Half conductor. What does half conductor mean? These materials, third group is, sometimes behaves just like a conductor, sometimes behaves like an insulator, depending on temperature. So we will study these in the 12th grade. This is the title of the 12th grade, which we are going to study in chapter 9. So this is a summary how we classify materials into three groups. Conductors is the first group, which conduct electricity by means of mobile electrons from one atom, jumping from one atom to the next one, to the next one, to the next one. Second group is insulators. Atoms of the electrons of the atoms cannot jump from one atom to the next one or next to next one. Good example is glass, rubber, silk, and plastic, and paper. Third group is semiconductors. They are sometimes conductor, sometimes insulator, depending on the temperature of the material, and will be studied in chapter 9. Okay, now let's continue with the potential difference, electric potential difference. I will make again, talk about the similarities between gravitational field and electric fields. And I will make the similarity between the gravitational electricity because they are not the same thing, but very similar. Their behaviors are very similar. So I will start with asking some questions to you about gravity. So assume that there are two identical masses, mass A and mass B. If I ask you which one has a greater gravitational potential energy, you can easily answer my question because you learned that. The one which has a greater altitude, higher altitude, will have a greater gravitational potential energy. You remember gravitational potential energy equation? Potential energy gravitational is equal to m times g times h. So m's are equal, g is the same, h. Which one is a greater? H, it will have a greater gravitational potential energy. Yani mass A has a greater altitude than mass B. That's why mass A has a greater gravitational potential energy. Everybody knows that. Yani A has a higher gravitational potential energy, B has a lower gravitational potential energy because their altitudes are different. What if I ask a question that if these masses are released, which one starts moving and in what direction? So give me an answer to me. Which one starts moving and in which direction? Of course, A will start moving. Everybody knows that. A will start moving, but in which direction? Oh, downward. So mass A starts moving downwards. Everybody knows that. So why? Why is it like this? You can answer my question. Gravitational force is taking A down. But this is one explanation. By using gravitational force, we can explain it. But there's one more method, one more way for explaining why mass A moves downward. Because as mass A moves downward, its gravitational potential energy decreases. And this is the behavior of every type of material. Every substance or every material when you release in air moves such that its gravitational potential energy decreases. Yani if any mass is released from rest, it starts moving so that it tends to decrease its gravitational potential energy. Now, think about river flow. River flows downward because water molecules move from a position of higher gravitational potential to a position to lower gravitational potential. So this is the direction of the water flow, from a position of a higher gravitational potential to a position of a lower gravitational potential. And there is a gravitational potential difference between these positions. That's why water flows. River, look at this river. So position A has a higher gravitational potential. Position B has a lower gravitational potential. So what happens to the water? It starts flowing from this position of higher gravitational potential to that position of low gravitational potential. So to make the water flow, there must be a difference in gravitational potential between two positions along the path of the river. Yes, Aya?
So, teacher, in order for the water to move, gravitational potential energy must decrease, right?
Exactly. That's why lake is all have the same level, same height, same gravitational potential energy. Is there a motion of the water in the lake? They don't move. Do they?
They're constant.
Constantly. They stay at their position. But river moves.
It's
Why?
flowing.
Because the gravitational potential energy changes. So always water tends to flow from a position of high gravitational potential to a position of low gravitational potential. So that's why we need a gravitational potential difference to make a water flow. Electric current is no different than this. Yani, their behaviors are same. Like what? Now follow. There are two conducting spheres with opposite charges. One sphere is positively charged. Second sphere is negatively charged. I explained shortly how we charge a material in the first lesson, but I didn't explain all of them because I don't have a time this. So two different spheres, conducting spheres, conductors, and they are charged oppositely. And when I connect these two spheres with a conductor, there will be electric current because one of the spheres is at a higher electric potential. Which one is positive? Positive spheres will have a higher electric potential. Negative sphere will have a lower electric potential, just like water flow. One position has a greater gravitational potential, other position has a smaller gravitational potential. So water flows from higher to lower. Similar thing happens in electricity as well. Sphere, positively charged sphere has a higher electric potential. Negatively charged sphere has a lower electric potential. When you connect these two spheres by a conductor or wire, electric current starts moving from higher electric potential to the lower electric potential, just like water does. So, in this case, and for water flow, we need a gravitational potential difference between two positions. For electric current, we need a electric potential difference between 2 points. Yani one sphere, here is positive, higher electric potential. Other sphere is negative, lower electric potential. So there is a electric potential difference between the spheres. And when there's an electric potential difference, electric current starts, just like water flow. So now I will continue on this basic. But we don't need spheres to be one of them is above, the other one is below for electricity. And you can keep them on the same level, just like this, because we care about electric potential, not gravitation in here. So positively charged sphere has a greater electric potential or higher electric potential. Negatively charged sphere has a smaller electric potential or lower electric potential. So there is an electric potential difference between the spheres. When we connect these two spheres by a conducting wire, so electric current will start from positive sphere to the negative sphere. So summary about the electric current. To set up an electric current in a conductor, there must be an electric potential difference between the ends of the conductor. Yes, this is one end of the conductor. This is another end of the conductor. Is there an electric potential difference? Yes. Why? Because one sphere is positive, the other one is negative. There must be an electric potential difference between the ends of the conductor. In this case, we can say that there is an electric current. Second, we can provide this electric potential difference by making one end of the conductor positive. So positive sphere makes this end positive. Negative sphere makes other end negative. So then we provide by this way electric potential difference. And third, direction of the electric current becomes from positive end, yani positive terminal of the conductor, yani from positive to negative terminal. And also we can explain that Direction of the electric current is from a point at higher electric potential to a point at lower electric potential. Now let's calculate the magnitude of the electric currents. So we got the direction. Now we will calculate its magnitude. Okay. Now if I ask a question, the amount of water current or water flow in a river is determined by number of the molecules in the motion. Yani if more molecules move, so amount of electric current becomes, water flow becomes more. If less molecules move, so water flow becomes less. Yeah, it depends on number of water molecules in motion. What do you think electric current depends on? Similarly, what is moving in electric current in water flow? Molecules are moving, but in electric current, electric charges are moving. So that's why the amount of electric current in a conductor is determined by the number of electric charges which are in motion. If more charges move, electric current becomes greater. If less electric charge moves, then electric current becomes smaller. Okay, these charges, electric charges, can be obtained in the nature by two types. Remember, one positive, one negative. So in a metal conductor, electrons are in motion. Just I explained, electrons jump from one atom to the next one, from next to next one, from next to next one. Electrons are in motion in metal conductors. So now I draw here two metal wire 1 and wire 2. Look at them. I draw a model. In one of the wire, charges which are in motion, 4 electrons are in motion. In another wire, 3 electrons are in motion. Now, if I ask you a question, which metal wire has a greater electric current? What is your answer? First one or second one?
First one.
First one, because more electrons are moving. So, first wire will have a greater electric current. Second wire will have a smaller electric current. We got it. So, in a conductor, metal objects, electrons are the charge carriers. They are called charge carriers. We will talk about this in chapter 9 again. Charge carriers. Yeah, they are moving. All electrons are moving. Remember protons? I told in the first lesson, protons are trapped inside the atom, inside the nucleus of the atom. They cannot move. All electrons are moving because they are free to move from one atom to the next because they are in motion around the nucleus of the atom. But there are some other conductors, solutions. In chemistry, maybe you studied about them, solutions. Salty water, for example, is a solution. In a solution, both positive and negative ions are in motion. And electric current is carried by not only positive charge, not only negative charge, but also positive charge. But these ions are moving in opposite direction. Positive and negative ions are moving in opposite direction in solutions. So now, why do they move in opposite directions? Now I will talk shortly about this. Remember, I told you that to make electric current, end of the conductors must be oppositely charged. One end must be positively charged, other end must be negatively charged. Remember, I put some spheres. One sphere is at one end, other sphere is at the other end. So this is say that positive sphere is in here. Here is negatively charged sphere in here. So electric current start from positive to negative. Okay? So, and also yesterday I explained you that if there is an electric charge, around this electric charge there must be an electric field. Yes, there's an electric field in this solution. Do you remember that electric field lengths start from which charge and ends at that charge I said yesterday? Electric field starts from positive charge and adds a negative charge. Yeah, when one end of this conductor is positively charged, other end is negatively charged, there will be formed an electric field in the conductor. And yesterday I explained, if you put a charge inside an electric field, this charge will start moving. And positive charge always moves in the same direction of the electric field, and negative charge always moves in the opposite direction of the electric field. This information is very important for chapter 9. So positive charge, when you put a positive charge inside an electric field, which are positive ions, they move in the same direction of the electric move, they move from right to left. But negative ions, they move in the opposite direction of the electric field from left to right. So that's why they move in opposite direction. Their behavior inside an electric field is opposite. My question is now different. Which solution now has a greater electric current? Tell me, which one? First solution or second solution? Which was a greater electric current? What do you think? No answer?
First solution.
The first one, of course, because there are 1, 2, 3, 4
More
charges are in
movement.
motion. In the second one, 1, 2, 3, 4 charges are in motion. That's why first solution will have a greater electric current. Second solution will have a smaller electric current. Okay, what about the direction of the electric current? In fact, we explained that. Electric current is from positively charged sphere to a negatively charged sphere. So, electric current, direction of the electric current is defined as the same direction of the motion of the positive charges. Yani, in which direction protons or ions are moving, electric current will be in the same direction. So this is determined conventionally. What does conventionally mean? I also explained this before. Yani, on our own, scientists define direction of the electric current as the direction of the motion of the positive charges. So electric current direction and positive charge direction are always the same. So as you see, this positive charge moves to the left, that positive charge moves to the left, so the direction of the current is to the left. However, electrons are moving in the opposite direction of the electric current. Negative charge, and electrons are negative ions, are defined to be moving in the opposite direction of the electric current. This is also very important for chapter 5. So, once again, direction of the electric current is defined as the same direction of the motion of positive charges, same direction of the motion of the protons, or same direction of the motion of the positive ions. But negative ions or electrons, which are negatively charged particles, are defined to be moving in the opposite direction of electric current. As you see on this in here, electric current is to the left, but direction of the negative ions are to the right. They are opposite in directions. This is very important. There is a question about this in chapter 5 section, chapter 2 questions. You should know this. Electric current directions are always in the opposite direction of the electron motion or negative charge motion, and always in the same direction of the positively charged particles or positive ions. Now, I will calculate electric current. This is the definition of the electric current. Electric current, symbol is capital I. Electric current, capital I, in a wire is defined as the rate, rate, again we met this, rate, divided by time interval. Something will be divided by time interval. The rate at which electric charges Q passes through a cross-section area of a wire. So, Q divided by delta T, in fact. Okay, a SI unit of electric current is ampere. It is the surname of one of the scientists, André Marie Ampere. So, here, this is a conducting wire. As you see, positive and negative charges are moving in opposite directions, and we know the direction of the electric current is in the same direction of the positive charges. And according to this definition, to get to calculate the electric current, I have to divide the amount of electric charge which passes through the wire by time interval delta T, which is the rate, because an electric current is equal to charge passing through a given area of the conductor divided by time interval that charge passes. If I write this equation by symbols, electric current symbol is capital I. Charge passing through a given area is delta Q. Q is the charge, delta Q, because as time passes, the amount of charge that passes changes. That's why we should write delta. Time interval is delta t. Delta Q over delta T is the equation for calculating electric current. These are the symbols. What is the unit of electric current? As I said, it is ampere. What is the unit of the electric current? We learned it's the coulomb. What is the unit of time? Which is second. 1 ampere is equal to 1 coulomb per second. Yes, we should know this as well. 1 coulomb per second is equal to 1 ampere. So this is the equation. How we calculate electric current. Delta Q divided by delta T. Delta Q divided by delta T is the equation for calculating electric current. Now, I will solve one problem, very simple problem to make it understandable. Exercise. Say that a total charge of 4 coulomb passes through a cross-section area of a nichrome wire in 10 seconds. What is electric current in the wire? So total charge that passes is 4 coulomb, which is delta Q. In how many seconds this charge passes? In 10 seconds, which is delta T. So what is electric current? Calculate I. So we know that I is equal to delta Q over delta T. And delta Q is, in this question, given as 4 coulomb. Delta T is 10 seconds. 4 divided by 10, which is equal to 0.4 ampere. So electric current that passes